So now that we understand what binary tree is, let us try to implement binary tree using the linked representation. So if you remember about linked list, we first defined the node in the list. So we'll do same thing for our binary tree. So first we'll define the binary tree node and what this should contain. Okay, this node should contain a particular value that it is going to store. So this value could be an integer, a character, a string, or any other complex data that you want to store inside your node. Okay, so we will not be specific about what type of value we store, but then what we need is we need an address of the parent. Okay, so again, to remind you with linked representation, what is going to happen out of the all memory from say 0 up to some large number, say a billion bytes that we have, certain block of memory would be given to represent a particular node, and the beginning of this node will be the address of this node. Okay, so when we represent a node, we store the value. So this value would be some part of the node. Okay, and then some part of this node will be used for storing various pointers which would point to other nodes. So for every node we need to know which node is left child, which node is right child. So what we'll need to store is again a binary tree node pointer, basically address of the left child. Let's call it left, and we'll also need a right child. Let's call it a right, and we'll also need a parent. Okay. So these are the three things that we will need. Okay, and that's what will be the data in our binary tree node. And now you can define various operations over this tree node, but we'll go and define them as and when required. Now let's define our binary tree. So when I talk about my binary tree, so just like linked list, all I will need is simply a pointer to a node. So I will have a binary tree node pointer, and I will call this as my root. Okay. And till now, if you are familiar with the operations that we define on our abstract data type, we should be able to create a new instance. So let's define create new operation on our binary tree, and we'll say that we have operation where we just create a blank tree. In that case, what we'll do is we'll simply say that our root is equal to null. So this is the empty tree that we create, a tree without any node. Okay. So once we have defined a particular empty tree, what we should do is we should try to add a new node in our tree. Okay. So what we should do is we should have a special function called add root. Okay, so we want to add something as a root to our tree, and it should give us, well, address, right? So I will say that it requires a binary tree node address, and let's call it a new node. And now what should happen is I should check if my tree is empty. Without that I cannot really add a new root. Okay, otherwise I have to deal with the replacement of everything. Okay, so we are saying that we start with the empty tree, and then we are adding the first node, and that's the add root. Okay, or to make it a bit more easy to understand, let's call it add first node. Okay, so this function is not about replacing the root or changing the root. This function is about adding the first node to your binary tree. Okay, so don't confuse it with replacing the root. We are talking about adding the very first node to our tree. And what should be the requirement for this? Before adding the first node, our tree should be empty. Okay, so we should check if our root is equal to null. If that's the case, then we should add, right? Then we should say that our root is equal to the new node that you just sent us, and then we should ensure that the new node dot parent is equal to null, and we should also set the left and right as null. Generally we would expect that the client node that sends us this node, it should do this adjustment before, but even if it has not done, we would do it on our own. Okay, so that's how our and then we would return. Okay, we are done, so we would return, but if that's not the case, then we should return an error. So that's our function add first node, and now we have to add the next thing is adding more nodes to the tree when tree already has some nodes inside it. Okay, so what we should do is we should define a function called add as, say, left child. Add a left child, and what it should receive, it should receive the address of parent node and address of the child node. Okay, so just for the sake of simplicity, I will simply write parent, and this is left child, so let's call it L child. Okay, and what this function should do, it should simply go to the parent and say that, oh, parent dot left will be equal to L child, and similarly L child dot parent will be equal to the parent. Here we are not checking if there is anything existing as a left child for the given parent. Okay, so if there is anything existing, that will be replaced. Okay, and we are not concerned if the L child itself has any subtree, any descendants. If they are, they get attached. That's the way this add L child function would work. And now corresponding, you can also think about add a right child function. Okay, so with these four functions, we can create an empty tree, we can create a tree with single node, and then once we have a tree with single node, we can go on adding nodes to our tree one after the other, or we can even go and attach a whole tree to existing tree. Okay, so now we can build our tree, and the question to ask is, now if I build such a tree, what is it that I can do with my tree? So here again we have to remind ourselves about what we did with the linked lists or the lists. So for lists, we said that we can create an empty list, then I can add element at the beginning of the list or end of the list. So similarly, we have the add element functions here, and once we created the list, we said that, oh, we want to delete an element from the list. Okay, so deletion of the element, we would delay a bit. We would discuss the deletion a bit later, but to delete or to search the values, first what we should be able to do is we should be able to traverse the data structure, right? So in case of lists, we said that to search, we would traverse our list, or to delete from the end of the list, we would traverse the list, or to print the list, we would again traverse the list. So traversal of the list was almost required everywhere. But in case of list, there was only one specific order, so we could do the traversal easily, if you remember, with single looping construct. But in case of tree, the traversal is not that straightforward. Okay, so before we define other operations on our binary tree, we'll first define how to do traversal of our binary tree.